solutions to the Force notebook problems or homework problems that are due November 29th. Remember, we got a test coming up Friday, December 2nd, and I think that'll be helpful to have that. This first problem, the reason they're numbered the way they are is they're out of the physics classroom, so I guess I put them PC. I'll also let you know what sections they were out of. I did modify a few problems, but most of them are almost identical. This one I think I modified because it was weird. The rocket and the person had a mass of 82 kilograms. I just thought that was weird. At any rate, so for this problem here, PC13, it's very much like one of the practice problems. So we've got two cables coming down. They're both at the same angle, so they're going to have the same tension in them. The tension is along the ropes themselves. The thing that we got to think about is vertical forces are going to equal 0. So said it was 43.1 kilograms. For all my problems, I used 9.8 newtons for G, for the gravitational constant. So I used 9.8 newtons per kilogram as G. You could also use 10. And a newton per kilogram is the same thing as, ooh, that's weird. You could also say meters per second per second. Those mean the same thing dimensionally. At any rate, so for using 9.8, I had to realize that it's the vertical component of each of these tensions is acting upward to oppose gravity acting downward. My gravity acting downward is the same as the weight of that thing, 422.4 newtons. I've got two cables, so it's not just T sine 34.5 degrees, which is the trig that gets me that vertical component, but it's two strings, so it's 2 times that. And if I'm in degree mode on my calculator, I get this, and I get 373 newtons of tension in each cable. These next three problems are pretty straightforward. The first one is an elephant and what's its weight, so it's just the mass times 9.8 newtons per kilogram. The second one is what would the weight be on the moon, and that would be less. That's 9,800 newtons on the moon. So remember that weight is not constant throughout the universe, but mass would be. So mass depends on the total number of atoms, protons, neutrons, electrons, stuff like that. And that's the same everywhere in the universe, and weight is just a form of force. For problem 6, it's asking you to find the net force on this person who's in the rocket sled. So we get the total mass multiplied by the acceleration. That gets us the net force, and that was 79,600 newtons. And that's Newton's second law. Newton's second law again for this one, but we're trying to find the acceleration, so I rearranged it to get A is equal to the net force over the mass, and that's 34.6 meters per second per second. For problem 14, this is where I think it's Logan's pulling his little sister. I hope he appreciates the fact that I used, his name, and I actually looked up his little sister's name on Infinite Campus to get it right. That's a lot of work. So I draw the free body diagram first, and even if you're not asked to do this, it can really help you think about things. So the normal force up is going to equal the gravitational force down. That said it was 304 newtons. The applied force was what Logan's pulling with. You could call that F pull, F Logan, maybe a tension, I don't know. And then the resistive force is friction, so that's 24 newtons. You don't need to put numbers on free body diagrams. I just did that since that information was given in the problem. So to figure out the mass, I take the weight and divide it by the gravitational constant, and I get 31 kilograms. Again, if you use 10 newtons per kilogram, you got a slightly different number. The net force is simply the difference between the applied force and the friction force, so that's 28 newtons. And the acceleration is that net force over the mass, so I got around 0.9 meters per second per second. Problem 17, you had an object, or a person basically, had some drag as they were accelerating down. I think a parachute had opened perhaps. So it said that the drag force was 108 newtons. It said the person's mass was 82.5 kilograms. So the first thing I'm going to do to figure out the acceleration is I need to figure out the gravitational force, which is the weight. So that's 82.5 times 9.8 gives me 808 newtons. Now, to get the acceleration, it's the net force over the mass. So gravitational force minus the air resistance over the mass gives me 8.36 meters per second per second. Hopefully it makes sense that this should be somewhere between 0 and 9.8 since the forces are acting against each other. The person's name who was jumping was Darren because he's daring. And as he goes faster and faster, this drag force will increase, but the gravitational force will stay pretty constant. Close to the Earth, that doesn't change much. So therefore the acceleration will decrease. Eventually this person's going to reach what we call terminal velocity, and that's where they have the same drag resistance as they have gravitational force of the weight. So P21, it says first draw a free body diagram here. So it didn't tell you to do that, but it helps me think about it. Because you're given the mass of the rocket and the acceleration, and you're asked to find the thrust. If you just multiply this by this, it won't get you the correct answer because there's another force acting on the rocket, and that's gravity. So the thrust has to be not only enough to accelerate the rocket up, but also to overcome gravity down. So when I draw this free body diagram, I realize that the net force is equal to the thrust minus the gravitational force. So the net force comes out to 4.77 newtons. The thrust is what I'm trying to figure out. The gravitational force I can get by using mg, so that's 1.02 newtons. So the thrust is actually 5.79 newtons, which is the force of gravity acting down plus the net force. Because so you need more force upward than just the net force, since gravity is acting downward. Last one here is problem 26. This is fun. So you should tell Mr. McCullough that I put him in a problem. And so we had push. I pushed him across the floor. There were some resistive forces or friction. Force the floor up, which is a normal force. Force of the earth down, which is a gravitational force. So that's the free body diagram. Something like that. Just make sure you label it. The net force, well, I was given the acceleration and the mass of Mr. McCullough. So the net force is 101 newtons. Now to find the frictional force, so that's what's asked in C, I have to use this equation which I've given you, and that coefficient of friction is equal to the force of friction over the normal force. Well, what's the normal force? On a level surface, that's equal to the gravitational force. So I can just put mg down here. So 0.35 is equal to the frictional force over this, which is 823.2 newtons. When I algebraically rearrange that, I get that the frictional force is around 288 newtons. So for part D, to find out my push, if I know that the net force is, or the force of friction is 288 newtons, and the net force is 101 newtons, the pushing force is going to be 288 plus 101. So I hope you can see how these last couple of problems, this free body diagram really helps me understand the math that I'm doing here. So this net force is equal to this minus this. That's exactly what's shown in the free body diagram. The same way here, the net force is equal to thrust minus gravity. That's what's shown in the free body diagram. So hopefully these help. Again, prepare you for your test. I don't care on your test if you use 9.8 or 10, by the way.